Okay, if we look at this iron 3 chloride plus ammonia, does that look like an AB plus CD reaction? Well, iron 3 chloride's AB because this iron 3 and chloride, AB. But ammonia is not a CD, it's not a compound in that sense. But the thing with ammonia is ammonia can form a little bit of ammonium hydroxide with water. And so with H2O can form ammonium and hydroxide. We'll just call it ammonium hydroxide. And so when we do this reaction, we do it like this because the FeCl3 plus ammonia plus water. And what we're going to do is we're going to take ammonia and water. Well, ammonia can collide with water. When ammonia collides with water, a little bit of ammonium is produced and a little bit of hydroxide is produced. And so this little bit of ammonium hydroxide that's produced, well, right here, ammonium hydroxide. So now we look, AB plus CD. Now it looks like an AB plus CD type reaction, double replacement. And so what forms here? Iron 3 hydroxide. What's the formula for iron 3 hydroxide? Okay, is that a solid or aqueous? Is it soluble or insoluble? What's the rule for hydroxides? Hydroxides are all insoluble except for group 1, ammonium, calcium, strontium, barium. So it's not one of the exceptions, so it's insoluble. It's going to be an insoluble solid. Okay, what's the other product? Ammonium chloride. Exactly. What's the formula for ammonium chloride? NH4 Cl, ammonium chloride. All right, now we have a driving force for this, and that's precipitation. For metathesis, precipitation is a driving force. For redox, precipitation is not a driving force. You know, redox has its own specific driving force. So let's balance it. How can I balance it? Well, it's easiest to balance it by the ionic compounds. 1 iron, 1 iron. I need 3 hydroxides here, so I'm going to get 3 ammonium hydroxides here. And that's going to make 3 ammonium chlorides here. So if I have 3 ammonium hydroxides, that means I need 3 ammonias and 3 waters. Give it to me. And so this is going to be the CE. The CE for this is going to be FeCl3 aqueous plus 3 ammonias, which will be aqueous, plus 3 waters, which will be liquid, yields FeOH, 3 solid, plus 3 ammonium chloride. That's a CE. What's the IE for this ionic equation? Or the TIE, total ionic equation. Okay, Fe3 plus Cl minus. And 3 minus.
And then H plus.
Plus H plus.
Plus H plus and O2. Or O minus.
Plus H plus and O2 minus.
Or would that be it?
Well, let's stop here for a second. You're ionizing everything, breaking it apart into ions, everything. Do we ionize everything? Or do we only ionize the strong electrolytes? Do we ionize everything or only the strong electrolytes? We only ionize the strong electrolytes. Everything else stays intact. And so iron 3 chloride, what are the strong electrolytes? The strong electrolytes are the strong acids, strong bases, and the soluble salts. And so iron 3 chloride is a strong electrolyte. However, I'm missing 2 chlorides. I have one iron 3, I have one of the 3 chlorides, but where's my other 2 chlorides? Yeah, it should be 3 Cl minus, and then I'm not missing anybody. Is ammonia a strong acid? Is ammonia a strong base? Is ammonia a soluble salt? Soluble salt would be an AB style compound. It's not any of those. So ammonia we don't ionize. We have to leave it alone. Is water a strong acid? No. Strong base? No. Soluble salt? No. So we leave it alone. We don't ionize it. Is iron 3 hydroxide a strong acid? No. Is iron 3 hydroxide a strong base? You would think iron 3 hydroxide is a strong base, but it's not. Why? Why is sodium hydroxide a strong base, but iron 3 hydroxide not a strong base?
Sodium hydroxide is soluble.
Yes, because sodium hydroxide is soluble. Do you remember the milk of magnesia stuff we talked about a long time ago? No? Drain cleaner versus milk of magnesia. Well, anyway, we talked about it before. And so this is iron 3 hydroxide. Here, solid. We leave it alone. Ammonium chloride, is that a strong acid? No. Strong base? No. Soluble salt? Yes. So we split it apart. What does it split up into? Yeah. Here, we split it up into NH4+. We don't break apart this ion. We split it up into the ions, which would be NH4+ and Cl minus. And then we've got to make sure we didn't lose anybody. And so we need 3 ammoniums and 3 chlorides. Make sure we didn't lose anybody. So the NIE, we get rid of the spectators. So let's go ahead and get rid of any spectators here.
So a strong base is a soluble base.
Soluble hydroxide.
Soluble hydroxide.
Yeah.
Only.
Only. No, there are others.
Like sulfide and oxygen.
Right. The strong bases are going to be the soluble sulfides, the soluble amides, which is easy because all the amides are pretty much soluble. Soluble oxides. Not all the oxides are soluble, like rust. Is rust soluble? Would you expect rust to be a powerful base? Not really, because the oxide's locked. You know, the oxide is a powerful base. If we look at the base chart here, it's the 3rd strongest. In fact, that's, very strong. But, that goes for things like sodium oxide, or, things that would actually dissolve. But things that don't dissolve, like aluminum oxide, this is not a powerful base. The surface of this is aluminum oxide. hydride and methides, the other ones there. And so something like drain cleaner, sodium hydroxide. An antacid contains magnesium hydroxide. Sodium hydroxide will kill you. This is drain cleaner. You don't want to be drinking drain cleaner, but you will survive if you consume some you don't want to consume too much, but you can consume some magnesium hydroxide and still survive. In fact, people do that intentionally.
What does that do?
It's an antacid for your stomach. So if your stomach is upset, we'll take it. Soothes your stomach. This would not soothe your stomach. This would cause some serious damage. Solubility. We talked about this solubility, milk and magnesia, way back when. So if you go back, you can take a look at that. But what's the NIE for this now?
All the ions reacting.
Yeah, well, did the iron 3 react? Is it a spectator or not a spectator? Iron 3, spectator or not a spectator? It's not a spectator. It's iron 3 on this side, but iron 3 hydroxide on that side. It reacted.
So spectator is what's not on the
Right, like chloride here. Chloride's a spectator because it's on both sides. Ammonia, not a spectator. It's ammonia on this side, which is base, ammonium on that side, which is an acid. Water, not a spectator. And so it looks like the only spectator is chloride. So the net ionic equation is going to be iron 3 plus 3 ammonia plus 3 H2O liquid produces iron 3 hydroxide solid plus 3 ammoniums. We can check the net ionic for balance. We check the atom balance first. 1 iron, 1 iron. 3 nitrogens, 3 nitrogens. 9 hydrogens plus 6 is 15 hydrogens. This will be 3 plus 12 is 15 hydrogens. 3 oxygens, 3 oxygens. So the atoms are balanced. But in addition to atoms being balanced, one other thing must be balanced. What is that? The charge. The net charge on the left. The net charge on the left is plus 3, 0, 0, so plus 3. The net charge on the right is 0, and then 3 times plus 1 is plus 3. So plus 3 plus 3. The charges have to balance on both sides of the equation. And so this looks good. This is balanced. And so we have the driving force here. The driving force is just the precipitation of the iron 3 hydroxide. So this is where, that partial reaction is important, because if we didn't have the partial reaction here, we wouldn't generate any hydroxide and we wouldn't get this metathesis reaction occurring here. And so what the point of this is, whenever you have aqueous ammonia participating in a metathesis reaction, we treat the aqueous ammonia as ammonium hydroxide to figure out the products. But we don't leave it as ammonium hydroxide because really it's 99.9% ammonia and water and only 0.1% ammonium and hydroxide. And if you go to the store to buy it, you have to buy ammonia and water. If you go to the store to buy it, you say, hey, I want to buy ammonium hydroxide. And what do they give you? They give you 99.9% ammonium water. And you go, hey, I didn't want ammonium water. I wanted ammonium hydroxide. And I want to return this. And they go, okay, give it back. And then you get the next one. You take it home and you find out it's 99.9% ammonia and water and 0.1% ammonium hydroxide. Why? Because ammonium hydroxide is not stable. And so we get that partial reaction. And so in other words, there's no way to get it. And so rather than doing false advertising, what you're doing is you're mixing it, ammonia and water. This is kind of what you're buying. These are the chemicals you're buying. You're buying iron 3 chloride and ammonium and water. So may it work. so this double arrow here, do you see this double arrow? This double arrow is showing that dynamic equilibrium occurring, you know? It's not showing you the percentages. Like, we can't tell, is it 50-50? What is it? You can't tell just by looking at this. Just the double arrow showing that there's, you know, partial reaction occurring. That's it. We can tell later, you know, when we get to chapter 18, I'll tell you how to tell. So we got forward reaction, and we got a reverse reaction, and we got some kind of competition occurring. Amphoteric, you already know that, right? Let's look at Lewis acid-base reactions. Lewis acid-base reactions, we need the Lewis structure to do it. Like, for example, BF3. BF3 is not a Bronsted acid because there's no hydrogens. You need hydrogen. This is not a complete Lewis structure. You know, they're getting lazy here. What are they missing in this Lewis structure? The lone pairs. I mean, that's some serious error. There are lone pairs on the fluorine, 3 of them on each fluorine, but boron has no lone pairs. In fact, boron has less than an octet. One way for boron to get an octet is to take it from some other molecule, like a Lewis base. And so in this case, the Lewis base is going to act as an electron pair donor to that boron. And now it has an octet. This boron has an octet. So this is a Lewis acid-base reaction. The formal charges are screwed up now, though. Boron's going to have a negative formal charge, and nitrogen is going to have a positive formal charge. But it's okay because now we got this octet. Nitrogen is okay with that positive formal charge, however, fluorine is not. And so this is an example of Lewis acid-base reaction. Lewis acid-base reaction is a bit more complicated, and so that's why we were focusing on Bronsted. And plus, there are lots of Bronsted acid-base reactions out there. And so these are the 3 definitions. Arrhenius is the least useful. Bronsted and Lewis are the 2 most useful. Lewis is the most useful, but it's harder. We can visualize all Bronsted acids as being Lewis acids and all Bronsted bases as being Lewis bases. It just requires, rather than transferring hydrogen, it requires a little bit more. And so we've been doing this. We've been doing the conjugates a lot, you know, assigning the acid and base going in the reverse direction, so we get conjugate pairs. Well, we also looked at the acid-base chart for conjugate pairs. So this is, you know, when we're looking at driving forces, we have to assign the acid and the base on both sides. You can see the pairs here, like for example, HA and A minus are a pair, B and HB plus are a pair. Those pairs are shown here. Here in the acid-base chart. Each acid is paired with the base. You know, these are conjugate pairs. This is the acid that's the conjugate base. This is the base that's the conjugate acid. There's a seesaw relationship. If the acid's strong, the base has got to be weak. If the base is strong, the acid's got to be weak. And so we see that seesaw relationship here. Strong acid, weak base. Strong base, these are going to be the weakest acids. Here. Here's an acid and water. Here, and this is also a partial reaction. Is there a driving force for this reaction? If we look at it, this is acetic acid and water. Acetic acid and water forms hydronium. You know, the acid loses the hydrogen, water gains it. So we form hydronium and acetate. Well, we compare acetic acid versus hydronium. Hydronium is stronger. So we're going from weaker acid to stronger acid. And then we compare water versus acetate. Water is a weaker base, acetate's a stronger base. And so there's no driving force because we're going from weaker to stronger acids and bases. However, this doesn't mean that we can't have partial reaction. And in this case, we do get partial reaction. The partial reaction is, oddly enough, it's similar to ammonia. It doesn't have to be, but it's going to be about 99.9% this and 0.1%. So we're going to get about 0.1% reaction, a little bit of reaction. Why? Because can we stop the collisions? No. It's going to result in a dynamic equilibrium. That's important because that's going to change certain things like the pH and whatnot. So we get a little bit of reaction. Now, a little bit of reaction changes the pH, makes the water more acidic. Okay, this is just looking at some conjugate. What is the conjugate acid of ammonia? Is ammonia. What is the conjugate base of bicarbonate? And so that means, what is the conjugate acid of ammonia? That means ammonia acts as the base. Bases take protons. What is the conjugate acid of, what is the conjugate acid and conjugate base of bicarbonate? Well, bicarbonate's amphoteric, this is ammonia. And so the conjugate acid of bicarbonate means bicarbonate's acting as the base. If bicarbonate acts as the base, it takes the hydrogen, forms H2CO3. If they're looking for the conjugate base, then that means bicarbonate's acting as the acid, so it loses the hydrogen. The bicarbonate can go either way, and act as an acid or act as a base. Now, what's the difference between a strong acid and a weak acid? Well, in terms of electrolyte properties, strong acids ionize completely. Weak acids partially ionize. And so, let's take a look at these two reactions in a different perspective. Actually, what time is it? Time for a break. Let's take a break and then we'll take a look at those reactions.